Hello all, this is Manoj Kumar Das, a faculty member of economics from Ravenshaw University. Today we are going to discuss the finitely repeated game and infinitely repeated game. As you know, in the last class, we have already discussed the extensive form of game, and today we will discuss similar aspects actually. What we are going to discuss will be detailed aspects that will also show to you. Now, if we look at this, today we will discuss finitely and infinitely repeated games. Now, what is the scheme of presentation? What are the things that we are going to cover here? This is the scheme of presentation. First, we'll discuss what is the repeated game, what is the meaning of repeated game. Then we'll discuss meaning of finitely and infinitely repeated game. Then we'll proceed to explain finitely and infinitely repeated game with the help of some example. Then we'll try to understand the payoffs and solutions of finitely repeated game. Then we'll note down some important remarks on finitely repeated game. Then we'll try to understand the computation of payoffs of infinitely repeated game. Then one of the important aspects of the infinitely repeated game that we'll discuss, which is nothing but the trigger strategies and good behavior. And at last, we'll discuss some remarks on infinitely repeated game. So if you will attend this lecture actually, if you will listen this, then this lecture will help you to know the meaning of repeated games, and this lecture will also help you to understand finitely and infinitely repeated game. This will also help you to know how to compute payoffs of finitely repeated game. Then to understand solutions of finitely repeated game. And you will also able to know how to compute the payoffs of infinitely repeated game. And you will also be able to know the trigger strategy and good behavior. So let us start our discussion. That is the meaning of repeated games. As you know, many strategic interactions, not in economics, but also in business, involve not just once, but repeated interaction over time among players. You can have a number of examples where repeated interactions take place. For example, in airlines, airline companies, they compete for business every day. And this competition go on every day, and this is a repeated interaction. Similarly, country engaged in international trade, they interact between different countries, interaction take place, and this interaction is repeated over the period of time. So repeated interaction is a game of long-term relationship where players interact repeatedly. So here what happens actually, here player's behavior can be conditioned upon the treatment she has received from other players in the past. It means our today's behavior against the other player is conditioned upon how we were treated in the previous period. Why? Because this is a repeated game. If we will do some harm today, this will affect the behavior of other player in the days to come. So that is why here the behavior conditioned upon the treatment one player received from other players in the past. So repeated interaction behavior obviously can be different from one-time interaction. In one-time interaction, what happens? We interact with other players and the game ends. But here what happens? We repeatedly interact, and this interaction may be helpful over the long run, and this may promote the cooperation, as we have already discussed this one in the last class. that how repeated interaction is different from one-time interaction. But here what we will focus actually, we will focus on finitely and infinitely repeated reactions. So players have more opportunity here to learn to coordinate their actions due to the presence of power of commitments. The attempt to reward or punish other players in the next rounds of interaction. It means if we do some harm today, then the other player may punish us, or if we'll help or coordinate the player in today's time, then the other player may reward us with some kind of actions in future. So here three aspects are involved. One, the attempt to reward or punish, and the power of commitment. This may promote the coordinated actions in future. So a player may be deterred from short-term advantages because of the threat of punishment that reduce our future payoffs. Now, what happens here? Here, a repeated game is also called as a super game, and it refers to a situation in which a normal form of game, that is also called a stage game, is played repeatedly by same players over discrete time periods. That is period 1, period 2, period 3, and so on up to period T. So the interaction take place repeatedly, and here a normal form of game or sub games played repeatedly. So a repeated game can be defined by a stage game G, which is played by players repeatedly for a number of times, say T. So here we can define formally the repeated game. Here the stage game G is a game in normal form, that is G equals to N SI pi I. What is N? Here N is the set of players, and here players number may vary from 1 to N. And what is SI? SI is the player I's set of strategies. And what is pi I? Pi I is player I's payoff function, and obviously it depends on the strategy choices available to player 1, 2, 3, and up to player Sn, which is denoted by capital S1, S2, S3, and so on up to Sn. So here, if the repeated game where the repetition is denoted as T, if it is finite, then we call the game a finitely repeated game. And if T is infinite, then we call the game as an infinitely repeated game. So here, infinitely repeated game and finitely repeated game depends on the number of times the game is repeated. If the game is repeated for a finite number of times, we have finitely repeated game. And if there is no end of the repetition, that means we cannot count, or we are unable to count the number of repetitions, then it becomes infinitely repeated game. So now let us understand this finitely and infinitely repeated game in more detail. So in the repeated game, the number of periods or the stages T can be finite positive integer, or T can also be infinite, representing perpetual interaction among players over time, where there is no end to the repeated interaction. Here T can be finite or T can be infinite. So if T is finite, then we call the game a finitely repeated game. Whereas if T is infinite, where the repetition game has no fixed end, then we call the game as an infinitely repeated game. So we can give a formal definition to the finitely repeated game. What is a finitely repeated game? A finitely repeated game, that is denoted as GT, is defined by a stage game G, which is played repeatedly for a finite number of times T. And here the stage game G is a normal form of game, that is G equals to that G involves actually n number of players, that is the set of players, SI, that is the strategy choice of player I's, and pi I, that is the payoff function of player I's, which depends on S1, S2 up to Sn, which is already defined. So this is the way we define finitely repeated game. Similarly, we can also define infinitely repeated game as above. But here you remember the t, that is the number of times the game is repeated, is infinite. That is the only difference between finitely and infinitely repeated game. So now let us take some example to understand what is finitely and infinitely repeated game. Consider the following normal form of the game. Here if you look at this, then here player 1 and player 2 has 3 strategies. Each one of them have 3 strategies, that is C, confess, N, not confess, P, that is partially confess. Similarly, player 1 has also 3 strategies. And if you look at this, if both player confess the crime, CC, you understand what is this prisoner's dilemma. So that is the reason we are not elaborating the rule behind this, as you already know. So here CC, that is when both confess, the payoff is 0-0. But if player 1 confess and player 2 do not confess, then player 1 gets a payoff of 2, whereas player 2 gets the payoff -2, and so on. And you can find out other situations like this. So this is one normal form of game. Now here, if this game is played t times, that means this game is repeated t times. At every stage, each player is informed about the previous choices made by both. Then the extensive form of this repeated game is depicted in this picture. If you look at this, player 1 and player 2 move simultaneously, and this is the symbol that shows simultaneous moves. Here player 1 has C, P, N, 3 strategies. Similarly, player 2 has 3 strategies C, P, N. Now here, if this game is repeated over the period of time and so on, and if it is repeated for up to t states, then this is called a repeated game. And here we have obtained the last number shows the payoffs of the players, and the source of this diagram is PK Datta. So I think you understand what is the repeated game. For more clarity, here you remember one point: the total payoffs, this repeated game is additive. That is, at the end, what we have written, this 0-0, this is the payoffs obtained by addition. That is, what is the payoff in first stage, what is the payoff in second stage, what is the payoff in third stage, and so on, what is the payoff in stage T. All these payoffs when added, then we get this payoff. So here, if CC played up to T stages, then the payoff associated with this will be 0-0. Now, if CN is played repeatedly up to T stage, then this will be 70 minus 2T. So this is the way we obtain by adding the payoffs. So I think you know how to obtain the payoffs here. Now this is example 2. And this example actually represents infinitely repeated game. So you see here player 1 has 2 strategies, C and N. Similarly, player 2 has 2 strategies, C and N. They simultaneously move here. And this game is repeated infinite period of times. That is the reason we have written here ... That means there is no end to this repetition. When there is no end to this repetition, this is infinitely repeated game. So now let us come to understand the payoffs and solutions of finitely repeated game. In case of finitely repeated game, the payoffs of finitely repeated game are obtained by adding the payoffs of the stage game. It means the payoffs are additive. That means if in the first stage the payoff is 3 and this is played for 4 times, then we have to add this payoff up to 4 times. That is 3 plus 3 plus 3 plus 3. This is the way we obtain total payoffs for finitely repeated game. And that is the reason the payoffs are additive. But what about the solutions of finitely repeated game? As you know, the solutions of finitely repeated game actually proceeds with the analysis of subgame perfect equilibria, which is done by way of backward induction. You remember here, we have already discussed the subgame perfect equilibria and the backward induction. And you have to apply the subgame perfect equilibria, or that is the backward induction, to solve a finitely repeated game. As you know, you will start from the end of the game. So recall from the previous discussion that this corresponds to the folding of repeated game, one subgame at a time from the end. And we have already discussed how to obtain subgame perfect equilibria and how to solve the game through backward induction. So those who have attended those 2 classes, they will also be able to solve a finitely repeated game. And that is the reason I am not discussing the solutions of finitely repeated game with the help of subgame perfect equilibria. However, we'll note here some important conclusions that emerge from subgame perfect equilibria. Now, these are the some remarks on finitely repeated game. The fundamental difference exists between the finitely repeated game, in which there is a unique Nash equilibrium and in which there is more than one Nash equilibrium. That means if we will solve the finitely repeated game, there you may get 2 types of solution. One, you may get unique Nash equilibrium, or you may get multiple Nash equilibrium. And there exists fundamental difference between these 2 types of Nash equilibrium, that is unique Nash equilibrium and more than one Nash equilibrium case. Now, what is the difference? In a single Nash equilibrium, how many times the game is repeated? It is immaterial because there is still only one subgame perfect equilibrium. In other words, the prospect of future interaction does not change players' behavior in any way when there exists only one unique Nash equilibrium. But if the stage game has multiple Nash equilibria, then there are many subgame perfect equilibria of the finitely repeated game. Some of them involve the play of strategies that are collectively more profitable for the players than the stage game Nash equilibria. So if there is more than one Nash equilibrium, there is always the possibility of sustaining good behavior in early stages of repeated interaction. That means there may be cooperation or coordination among the players. So this good behavior is sustained by the prospect of better future play than that which follows short-term opportunistic behaviors. So now let us proceed to understand infinitely repeated game and how to solve it and how to compute the payoffs of infinitely repeated game. So when a game has no identifiable end, that is when t is infinite, we have infinitely repeated game. And in this case, we cannot simply add up payoffs to obtain total payoffs. So in case of infinitely repeated game, we cannot add the payoffs. Why? Because there will be 2 problems. First one, the payoff numbers may add to infinity. When you will add infinite number of times, the payoff numbers may add to infinite. And here there will be one problem, that how to compare between 2 infinite to solve the game. Then the second problem is the number may not add up the same way for every t. So for every stage, we may not add up the same number in similar way. So these are the 2 problems for which we cannot add the payoffs in case of infinitely repeated game. So there is one way out to solve this problem. Therefore, here discount factor is introduced where payoffs are discounted to get their present period equivalent. So you will look at this game. or one example, when the stage game payoff are 1 in every stage, if 1 is the payoff that is constant for every stage, then the total payoffs is 1 plus sigma. Sigma is the discounting factor, then plus 1 into sigma square plus 1 into sigma q dot 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 plus 1 into sigma t plus dot dot dot. So this is equal to 1 by 1 minus sigma, where sigma is the discount factor. So payoffs of infinitely repeated game is obtained by discounting the future payoff. So the payoffs to the finitely repeated games are computed as follows. Suppose that at the tth stage, player I gets a payoff of pi I, and the total discounted payoffs for player I then is pi I0 plus pi I1 sigma plus pi I2 sigma square and so on, where sigma, sigma square, etc. are discounted factor. That means our future payoffs are discounted by a factor that is called sigma. So this total now cannot be infinity, and it always adds up. So the problem is solved when we introduce discounted factor. Further, after addition of sufficient number of stages, the total remains virtually same. Why? Because after sufficient addition, then the future payoff, when it is too long, that is virtually immaterial to us, because we will not give value to a long future payoffs, which may be treated as 0. That is why after a sufficient number of addition of the stage payoff, the total remains virtually same. And for example, when the stage game payoffs are a constant, say P, then the total payoff is equal to P by 1 minus sigma. Like when total payoff is constant 1, we have obtained there 1 by 1 minus sigma. Here, similarly, if payoff is constant P, then it will be P by 1 minus sigma. So now this is the way we have obtained the payoffs of infinitely repeated game. Now let us understand what is trigger strategies and what is good behavior. So to understand this, let the following prisoner's dilemma stage game is played period after period with no clearly defined last stage. That means this prisoner's dilemma game is repeated infinite number of times. Now here what will happen? Here the payoff to player is the total discounted payoff as obtained by the earlier equation. You know how to obtain this? So you can obtain its discounted payoff. And here player continue to play NN, that is NN coordinated action. Player will continue to play this one if no player confess at any stage. So this coordination will continue till no player confess at any stage. But if one player will confess, let player 1 confess and player 2 is still playing N. Now player 1 will immediately get a payoff 7, but subsequently it will get 0 payoff. Why? Because player 2 will also go to confess in the subsequent phase, and CC will form next Nash equilibrium where 0, 0 will be the outcome. So if either player confess at some stage, then both players CC, they play CC from the subsequent stage onward. This is a strategy which is called a green trigger strategy. Why? Because once we deviate from NN to C, then CC will be played forever. And that is the reason deviation from NN strategy is called green trigger strategy. That is a deviation from the desired behavior NN triggers a switch to a punishment phase where CC strategy is played forever. The trigger is a green in the sense that once the punishment phase is initiated, this punishment phase is never revoked. So let us look at green trigger strategy for subgame perfect equilibrium. In the infinitely repeated game, there are infinite number of subgames, as you know. After every stage of play, no matter how those stages were played, a new subgame will start. So to find out subgame perfect equilibrium, we have to check out every one of these subgames for equilibrium, that whether these subgames are in equilibrium or not, we have to check it. But the problem here is we cannot find for all subgames because the subgames are infinite in number. So if the subgames are infinite in number, how to solve that infinite number? That is the why we have other way to proceed. In the above example, for the green trigger strategy, there are two kinds of subgames. One type of subgame where the subgame that follows the repeated play of NN strategy in the first T stages, and second variety of subgame, that is every other subgame where CC strategy will be played, and this is shown as below diagram. Now if you look at this, up to this actually, up to this stage T, we look at this. Here NN strategy is played by the players, and once they deviate, one of them deviate from NN to let's see, then CC forms the other strategy combination, and that is played. So this is one stage game where NN is played, and the second type game where CC is played. Now let's solve for type 2 first, then we'll solve for type 1. For type 2, where CC is played forever, and this is also Nash equilibrium. No player here can increase his payoff in any stage by playing N against C. So if one player is playing C, and if you will play N, then your player payoff will be -2, and the other player's payoff will be 7. So if CC is played, if you will deviate, then you cannot increase your payoff. So CC is also Nash equilibrium in a type 2 game. Now for type 1, what happens here? If a player deviate by confess, then immediately what he will get is immediately it will get 7 payoff, and subsequently it will get 0 payoffs. So staying with NN strategy would yield this player a payoff 5 in the current stage as well as a stream of 5 payoff in every future period. Hence, the total payoff to staying with NN strategy is 5 plus 5 sigma plus 5 sigma square plus 5 sigma q plus ... And the total will be 5 by 1 minus sigma. And this procedure we have already discussed, how we obtain the payoff. Now here what happened? So staying with the green trigger strategy will be better if 5 by 1 minus sigma is greater than 7. Then you will stay with NN strategy. Otherwise, you will move to CC. Now, it means what happens? If sigma is greater than 2 by 7, then you will stay with the NN strategy. Otherwise, you will leave it. So nice guy behavior, both player always play NN and neither tempted of confessing, provided there is not too much discounting. Exactly the opposite of the, this is exactly the opposite of the nasty guy behavior. Both players always play CC, and the CC happens in case of a finitely repeated game. So niceness is sustainable in infinitely repeated game because at every stage it is possible to make a conditional nice guy promise. If you are nice today, I will be nice tomorrow as well. And if you are not nice today, I will also not be nice tomorrow. So the accompanying threat is that if you are nasty today, I will be nasty forever after. This stick carrot is a sufficient deterrent if the future matters. The threat of the grim punishment might help achieve other behavior as well. Thus, nice guy behavior might be achievable with different and less severe punishment. There are in fact many achievable behavior in the infinitely repeated prisoner's dilemma. So if the future punishments and rewards are sufficiently large, then we can induce the player to play today in a variety of ways that they would not otherwise. Both good behavior with strategy NN always and more whimsical behavior altering between NC and CN can be sustained by sufficient significant future. So in case of infinitely repeated game, any outcome is possible. So this is all about today's class. Thank you. For better future, as you know, keep learning, go green, and plant tree, save water. So thank you very much for today. This much. Thank you.